Hi, kids. I'm gonna teach you guys a little bit about electrostatic potential energy. So in order to do this, first we're gonna review gravitational potential energy and how that goes. So let's say we had a pretty typical problem where you have a skier that's going down a scary hill here. There's my skier, okay. And our skier is going to be going from point A to point B. And if you guys remember, how do we do these problems? So let's say the problem is like, hey, how fast is the guy going at the bottom? So then you would say, well, you would go from A to B, and you would say, well, if they start from rest, so we'll say our initial velocity is rest, then at this point you have potential energy. At this point you have kinetic energy. If we say the hill is frictionless, then no work was done, so you have mgy, where that was our h, or mgy, equals 1/2 mv squared. And hey, you know what? The mass doesn't matter, and then you could solve for the v. Hopefully you guys remember how to do that. And you could solve that, no big deal, no big problem. This was, though, near the Earth's surface. Remember, near the Earth's surface, g is constant. It was a constant 9.8 meters per second squared. If you're doing problems where you're not near the Earth's surface, well, it's a little more complicated. You know, if you remember, you have a situation where, here's the Earth, and you have a rocket ship, and this rocket ship is moving away from the Earth, or maybe the rocket ship, there's some random thing that's going to fall into the Earth, bad news. If it was something like that, again, you would say, hey, I want to label my point. So if I'm going to say I have this random object that's way out here in outer space, and then later on it's going to fall into the Earth, and you would say, all right, well, remember, universally, g is not constant, and that was where you had to use this equation. Hopefully you guys remember this. The GMM over R equation. Remember the negative. The negative is there because the only place that you have zero potential energy is where you have zero gravity, and you have zero gravity when R is an infinite distance away. And maybe your AP Physics 1 teacher demonstrated that using spandex, and showing that, hey, you know what, that if I have a mass hanging like this, the edge of this represents my really far away distance when r is infinity, and anything closer is less than that, so it's underneath zero. And you might think, well, geez, why are we even talking about this with charges? And I'll explain in just a minute. But hopefully that you guys remember all that stuff. So like here would be, if I was setting up this problem, because this is going to be kind of similar to with our electrostatics, it would be like, all right, if I call this A and this B, well, going from A to B, you would have UG at A, you would have UG plus kinetic at B, and it would be a different UG. There's no work done because we're in outer space. There's no friction. And then you would have to set up your equation where it would be negative GMM over R, negative GMM over a different R, 1/2 mv squared, and plug stuff in and you could solve. All right, so now let me explain how this would work with charges. Okay, so, all right, so here's how this is going to work with charges. The electrostatic equivalents to mass, so like, it's kind of like, hey, with electrostatics, and then we have, gravity stuff. Well, mass is like charge. So Q, or little q, okay? So where we have mass with gravity, we're going to have Q's, okay? Where you have big G for the gravitational constant, which was on our handy-dandy formula sheet here. Big G on right there. Okay. The electrostatic equivalent is going to be K, which this is kind of stupid on this formula sheet, but if you look Let me find it. 9 times, right there. All right, so it's this one right here. But for some reason in AP2, the College Board does it where they have 1 divided by 4 pi epsilon naught equals k. We're just going to say k because that makes more sense. So k is equal to 9 times 10 to the 9th and whatever the units are. So just remember, you know, if you think about our formula here where you had UG equals negative GMM over R, not over R squared, just over R. Well, over here, you're going to have UE equals K instead of G, QQ instead of mass over R. And then you would solve, okay, you could solve this way. There really isn't a negative sign, and let me explain why. Gravity always attracts. This sometimes attracts, it sometimes repels, as you guys know. So this is really what our equation is going to be. But let's say we had a situation where it was like this. You have some positive charge Q sitting here, and let's say, I don't know, I have a little charge plus Q sitting there. Maybe that little charge is a proton, maybe it is, I don't know, whatever, but there's a smaller charge sitting there. If I hold it close and then I release the little charge later on, that little charge is going to be moving that way. If I was to do my equation just like we always do, hey, here's my A, here's my B. At this point, I have UE. Over here, I have UE plus kinetic energy. And then here would be KQQ over R. Here I would get KQQ over a different R. So like, I'll call this R1 and R2, where this would be R1. This would be R2 plus 1/2 mv squared. And if this was, for example, a proton, well, you could do this problem because assuming we know how big Q is, we know how big little q is, we know the mass of a proton, and you could plug stuff in and solve. But this would be like, hey, they're repelling. Now, with gravity, there's not really in real life an equivalent to this, but we can come up with kind of an imaginary equivalent to this, which would be kind of like anti-gravity. So if I show you guys my spandex here, let me move this back a little bit, and I was to put this underneath, and you can imagine instead of a gravitational well, I have a gravitational hill, so that if I put a marble here, it's going to roll down. This would still be represent 0, but this would be positive energy, whereas when we're doing really with gravity, that's negative energy where it's underneath. So this would be like anti-gravity, you know, in sci-fi movies where they talk about anti-gravity, you know, and anti-particles or whatever, that would be that, okay? Or dark energy, same idea. Okay, but more importantly, hopefully that makes sense with electrostatic charges. If I was to let this keep going, eventually what would happen is that if this was super far away, so I let it keep going, eventually this would be 0, and I would just have, hey, whatever potential I started with, it gets converted to kinetic energy if it goes far, far enough away. Okay? Hopefully that makes sense. The only thing you have to be careful of, well, what happens if you have opposite charges? Well, if you have opposite charges, they're going to attract. So, for example, if this was a negative Q, if that's what I'm starting with, well, then later on, this thing is going to be moving towards it. So it would be like, hey, I start with UE, and over here I have UE plus K. But if you were to plug it in, KQQ over R equals KQQ over R2 plus 1/2 mv squared. Just keep in mind, if this is negative, this number is negative, this number is negative, that, hey, you know what? This would be a smaller negative number. Why? Because here, this would be a bigger negative number, so that you can see that, well, when I say bigger negative number, this would be like maybe -1, and this would be -2. So I have lost potential energy, which means this would have to be +1, so I gain kinetic energy. Okay, that's the only thing you have to just keep in mind. And the equivalent of that would be, if you think about the spandex. Okay, that in this case it would be like I am doing this. Okay, that would be, and if I have a charge here, it's going to roll down. It's going to roll towards it. Where if I was to do my previous case, it's going to be like this, so that if I have a charge sitting on top, it's going to roll away. So attract versus repel, and you should be good for doing the packet pages now. All right, bye kids.